Okay, Guillaume l'Hôpital, right? It looks like hospital, but there's no S in it except at the end. Pronounced l'Hôpital. Guillaume, where's he from? You can tell by his name. He is from France, right? But he stole the rule from somebody in Italy, okay? So I think I told you this story last year. The same thing as between Leibniz and Newton. Whoever publishes, that's whose name gets attached to the rule. So to give credit where credit is due. So John Bernoulli, right? He was in Italy, an Italian mathematician. Okay, so he developed a way to deal with indeterminate forms of limits. Guillaume l'Hôpital got a hold of it, published it, gave credit to John Bernoulli in his work. So he did say, from John Bernoulli's work we did know this. But John never published it originally. So the only place it was published was in L'Hôpital's work. And so people didn't want to say, hey, where L'Hôpital quoted John Bernoulli and he said this, and it just became L'Hôpital's rule, even though L'Hôpital really did give credit to John Bernoulli when he wrote it down. So we know it is L'Hôpital's rule now, and it's a way to deal with indeterminate forms. So first we have to start with what in the world is an indeterminate form. There are several. I'll list the most common. Okay, you have been taught your entire mathematical life that any number divided by itself will always equal what? Except
0.
Okay, and? Infinity. Okay, so any number divided by itself will always be 1 unless you come up with 0 divided by 0 or infinity divided by infinity. These are the two most famous indeterminate forms of numbers. They are not, it does not mean does not exist. It does not mean, imaginary numbers. It does not, anything you can come up with, it is called an indeterminate form, and it is not satisfactory as a final result. You can't just stop there. You can't just write DNE and then keep going. Okay, there is a rule now to deal with that. What if you get that as an answer, what do you do? Other indeterminate forms have to do with multiplication. You've also always learned every time you multiply a number by 0, you get 0. Except when you multiply 0 by infinity. That is not 0, and it's not infinity either. Okay, that is indeterminate. Okay, and so you can't say what is it. It doesn't have a numerical value. It is simply called indeterminate, and you need a way to deal with that. Another is subtraction. Yes? This is just a new indeterminate form. Okay, so there are indeterminate forms. Maybe I can label them. There are division indeterminate forms. There's multiplication indeterminate forms. And there's a subtraction indeterminate form. Because you've always been told anything minus itself is going to be 0, except for infinity, because you can do infinity minus infinity and still have infinity left. Right? You can take infinity away from infinity and still have infinity left over. So that is also called an indeterminate form. All right, so how do we deal with these? And this is where L'Hôpital's rule comes in. All right, so if the limit comes out to an indeterminate form, limit comes out to an indeterminate form. We apply and reapply. So that means we can do it over and over and over again. L'Hôpital's rule. Until we get a determined answer. So the opposite of indeterminate is determined. And we'll just keep doing L'Hôpital's rule over and over until we actually get something that works out. All right, so what is L'Hôpital's rule? L'Hôpital's rule is that the limit approaching f of x divided by g of x equals, approaching a, as x approaches a of f prime of x over g prime of x and if that's still indeterminate, then that would equal the limit as x approaches a of f double prime of x over g double prime of x. And if that's still indeterminate, it just keeps going. Assuming that you started with an indeterminate, right? This does not apply if the first time you do it, it's not indeterminate. Okay, so we have to assume that that value is indeterminate to begin with. So that is L'Hopital's rule. If the original value of the limit in a quotient form comes out to be some kind of indeterminate number, either 0 over 0, infinity over infinity, or one of the other ones with subtraction, you have to rewrite it in a fraction form and then do successive derivatives. This is not the quotient rule, bless you. Okay, this is not the quotient rule. Quotient rule is something totally different. The quotient rule is how we find the derivative of a function in quotient form. This is how we find the limit of something if the original limit is indeterminate, but we use derivatives to do it. So in an ideal world, I would have taught you this in the limit chapter. But in the limit chapter, you didn't know derivatives yet. So you have to wait until after you finish some derivatives before you can do this. All right, so this is L'Hopital's rule, so let's practice it. Okay, so let's evaluate the limit as x approaches 0 of the function 3x minus sine of x over x. You have to show that this would be an indeterminate problem. So 3 times 0 minus the sine of 0 over 0. That comes out to be 0 over 0. You have to explicitly come to the conclusion that it's indeterminate before you move on to L'Hopital. That's one of the FRQ requirements. Okay, it's like using intermediate value theorem or mean value theorem. Like you have to state that it's continuous and differentiable before you can do it. You've got to state it's indeterminate before you move on. No, if the numerator is anything else, then anything else divided by 0 is infinity. Okay, it's only 0 divided by 0, that's a problem. Okay, just like when you have infinity, anything else divided by infinity is 0, except infinity divided by itself. Yeah, Megan?
So in homework, do we have to do this every time, show that it's indeterminate?
Well, yeah, because some of them aren't. And then you would have wasted your time.
What if it tells us to use the rule?
No, then you can assume that they, yeah.
And so if it isn't indeterminate, will we just put as indeterminate and just 0?
Yeah, if it isn't indeterminate, if it's an actual number, then just say the number.
Okay.
Yeah, what it is. Okay, so let's apply L'Hopital. So we'll continue. And so we just take the numerical derivative over the numerator derivative and the denominator derivative. So the numerator derivative is 3 minus cos of x, and the denominator derivative is 1, and then we plug 0 into that. So that'll be 3 minus the cos of 0 over 1. The cos of 0 is 1. Oops. And so we actually get a numerical answer, and we get 2. So that means the answer to the original limit was 2. Okay. All right, so evaluate another one. Okay, any questions so far? Especially for, like Justine, I know you've never seen this before, right? Irene, Joy, never seen this before either, okay? All right, so just stop me if you need me to back up. All right, so how about the limit as x approaches 0 of x minus sine of x over x cubed? So again, we show that 0 minus the sine of 0 over 0 cubed is 0 over 0. So once again, we have an indeterminate form. So then the process can continue with L'Hopital. The derivative of x minus sine x is 1 minus cos x over 3x squared. When I plug 0 into that, I get 1 minus cos of 0 over 3 times 0 squared. That's 1 minus 1 over 0. That still comes out to 0 over 0, which means we rinse and repeat, and we do it again. As long as it comes out to be an indeterminate form, you can continue to apply L'Hopital. So the derivative of 1 minus cosine x is positive sine of x over 6x. Plug 0 into that. Sine of 0, 6 times 0, 0 over 0. So thankfully, we have L'Hopital that will help us out. One more time. The derivative of sine of x is cos of x. The derivative of 6x is 6. That will be the cosine of 0 over 6. So 1/6 is the numerical value of the limit of the original problem. Well, we have to do some subtraction ones. Okay. The hard part of this is going to be the algebra. It's hardly ever the calculus. It's almost always the algebra. Okay, so let's take the limit as x approaches 1 of 1 over the natural log of x minus 1 over x minus 1. All right, direct substitution is going to give me 1 over the natural log of 1 minus 1 over 1 minus 1. Natural log of 1 is 0. So we have 1 over 0 minus 1 over 0, which is infinity minus infinity, which is another indeterminate form. So I need L'Hopital, but L'Hopital only works on an original problem that's in fraction form, not subtraction form. So this is where you're going to need to do algebra to the original limit before you can apply L'Hopital. And so what do I need to do to that original limit to get it in the form where I have a distinct numerator and a single distinct common denominator? Okay, I need a common denominator. So this is where you're going to need your algebra skills to be pretty tight. And so we'll have x minus 1 minus the natural log of x. Say that again? Oh, thank you. And my common denominator is the product. Don't worry about multiplying that or anything. Now we're going to apply L'Hopital to this. And so we'll have the derivative of x, which is 1, the derivative of negative 1, which is 0, the derivative of the natural log of x, which is 1 over x. And then how are we going to do the derivative of the denominator? Not chain rule, product rule. So my product rule is going to say x minus 1 times 1 over x plus ln of x times 1. We might want to just clean that up a tiny bit, the denominator. So I think it might look a little better if we had written this as 1 minus 1 over x plus ln of x. That's our denominator. And 1 minus 1 over x is our numerator. All right, we'll plug 1 into that. We're going to get 1 minus 1 over 1 minus 1 plus 0. So I get 0 over 0 again. Did I go too fast?
No, I was
Oh.
complimenting her on her pen colors.
Oh. All right, so then one more time. So the limit of the derivatives again. So the derivatives of the 1's are 0. The derivative of negative 1 over x is positive 1 over x squared. So I have that twice. And then the derivative of the natural log of x is 1 over x. So here finally I'm going to get a actual number. So I'm going to get 1 over 1 plus 1, 1/2. So that's a subtraction one. And then we just have to do a multiplication one, and then we're finished. And if those of you then who need to leave for basic can go. All right, so any questions so far? We saw 0 over 0. We've seen infinity minus infinity. And now we need to do a multiplication example. So here's our multiplication example. The limit as x approaches infinity of 1 plus 1 over x to the x. This is the indeterminate form that bothers people the most. What happens if I plug infinity into this? I'm going to get 1 plus 1 over infinity to the infinity. Okay? All right, well, what's 1 over infinity? Okay, just about 0. So then we'll say 1 plus 0 to the infinity. And this is, so 1 to the infinity. And everything about you screams that you just want to say 1 to the infinity should be, it should be 1. Okay, it's not. Okay, it's not. Okay, so the definition of this is an indeterminate form. Okay, because it's not really 0, is it? Okay, it's not really 0. It's 0 plus. And so this isn't just truly 1 to the infinity, it's 1 plus a little bit to the infinity. So this is considered an indeterminate form. All right, so let's go back to this. You've seen this recently. You just took a test on it. What did you do to something that was in this form? Okay, we used the ln. Okay, when you've got x in the power, okay, so we're going to use ln. All right, so we are going to apply ln to the whole thing. All right, so from here on out, I'm going to zoom out a second. For everything I do now, for a while, it's on the assumption I've applied an ln. So then when I get to the end of that work, what am I going to need to do? I'm going to have to undo that ln by applying an exponential e to undo it at the end. Okay? All right, so we're applying an ln. What that means is that the limit now has x in front Okay, all right, so I've got a product, which will now be, if I plug that in, I'm going to get infinity times 1 plus 1 over infinity. Where's my ln? Infinity times, there we go, times ln times 1 plus 1 over infinity, which is infinity times 0, which is another indeterminate form. Now, have I actually done L'Hopital yet? No, I've only applied an ln. I haven't done L'Hopital. So I need to do L'Hopital. What form does the problem need to be in? Okay, it has to have a denominator. So instead of multiplying, we can make it division, right? We do that. Division is the same as multiplying by the reciprocal. So then multiplication is the same as dividing by the reciprocal. Works the same way. Okay, so if multiplication is the same as, or division is the same as multiplying by the reciprocal, then multiplication is the same as dividing by the reciprocal. And so we're going to keep this one on top, and we're going to divide by the reciprocal on the bottom. Now I can apply L'Hopital's rule because this is a fraction. And so I can take the derivative of the numerator and the derivative of the denominator. All right, the derivative of the numerator is 1 over 1 plus 1 over x times the chain rule on that, which would be negative 1 over x squared. That's the numerator. What's the derivative of the denominator? Also negative 1 over x squared. Yay! Okay. So I get to reduce.
Oh,
Yeah.
Isn't that lovely? And then I can plug infinity right in. So we get 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0, which is 1.
it worked.
Wait.
But then you have to add in.
Okay, but that was all based on the fact that we did that by applying the ln. So now we have to undo the ln. And so the answer is not 1. The answer is e to the 1, e to the first. And so the answer, the limit value, is e to the first, or e. It's like you struggle and you slog through some algebra, and then all of a sudden, whooshoo. It's like when we get to u substitutions and we have that perfect u substitution, and then everything reduces away. Okay, all right, there we go.
Wait, so wouldn't the answer just be e then?
Correct, e to the first, e, yeah.